Hi, this is Zachary from PPP. I'm one of the organizers of Plaid CTF, and this year I wrote a challenge called the Watness 2. It was a sequel to last year's problem, the Watness, wherein players had to reverse engineer a WebAssembly implementation of Jonathan Blow's The Witness. It was a lot of fun to build, so this year I wanted to try something slightly different. Instead of using a brand new technology like WebAssembly, I decided to take things back a bit and use a really old technology called HyperCard. Since it was a lot of fun and I learned a lot while doing it, I wanted to spend a little bit of time talking about what HyperCard is and how I built the Watness. If you're interested in following along, you should install the following software: SheepShaver Virtual Machine, macOS 9, HyperCard 2.3, QuickTime 4, and Macintosh Programmer's Workstation Gold Master. Additionally, it might be useful to install ResEdit, any version, or StuffIt Pro. These aren't required, but they're things that I used and might be helpful if you're trying to understand more about how the problem works. Before we go into too much more detail about how everything's set up, let's talk a little bit about HyperCard. This problem was largely inspired by an interview Rand Miller gave with Ars Technica earlier this year. In it, he describes how the Cyan Worlds team was able to use HyperCard to develop the original Myst game. Now, HyperCard was a technology developed in 1987 by Bill Atkinson at Apple. It drew largely on the work of Doug Engelbart and Ted Nelson, who in the 60s proposed ideas for showing branching information. HyperCard is a combination UI framework and database that allows application developers to build complex apps with branching logic. Given that the theme for Plaid CTF this year was Ready Player One, a story that draws heavily on nostalgia, we decided to have some nostalgia of our own. As such, I decided to demake 2016's The Witness using this technology, similar to 1993's Myst, and thus the Watness was born. In order to understand how the Watness was made, we first need to understand the levels of abstraction that HyperCard uses. At its base, everything is a stack. Even the home application you see here is just a stack that was developed in HyperCard. Stacks are comprised of several cards, and cards can contain several components. These components could be text nodes, they could be buttons, or they could even just be drawings. HyperCard uses a scripting language called HyperTalk. Let's go ahead and enable that now so we can play around with it. HyperTalk is a Smalltalk dialect, and so it revolves around the idea of passing messages around. Specifically, you can send a message to one of the components that I mentioned. It will either consume the message or do something with it and then bubble it up the stack. For web developers, this is very similar to how events are passed in the DOM. Okay, let's go ahead and create a stack so we can start playing around with it. Because HyperCard is mostly geared toward non-technical users, it comes with a number of built-in graphics utilities. You can see me using several of them here. In addition to graphical utilities, it also has a number of built-in components as mentioned earlier. These components include text inputs, backgrounds, and buttons. Buttons specifically are the primary interaction component used by HyperCard. They can be scripted using HyperTalk so that when the user clicks on them, they perform some action. For instance, we can set it up so that when we click on it, it sends a message to the user, using the answer command in HyperTalk. You might have noticed, but HyperCard only supports black and white. For anything resembling a modern game, this isn't really going to work. Fortunately, it comes with a built-in plugin called Color Tools. You can install Color Tools from the home screen by clicking here, and then here. Once Color Tools is installed, it gives you access to the color menu, which among other things allows you to embed images into the stack. With QuickTime 4 installed, you have the ability to load JPEGs directly. But there's a problem. If you just load a JPEG, it doesn't store the image on the stack, it just stores a reference to it. So when you start the stack up, you need to tell it where to find the image. For a game, this isn't really feasible. Instead, we can use something called a pict file. A pict file is just a container format that contains a bunch of serialized opcodes for the QuickDraw library. Among other things, it can be used to store JPEGs. Fortunately, Color Tools has the ability to convert JPEGs to pics for us. Unfortunately, this process is a little bit tedious. It requires you to first try and load the JPEG as a pict, let HyperCard get confused, automatically convert it for you, ask you where it is again, delete it, and then re-import it as a pict file. If you go through this whole process, you'll generate a pict file from the JPEG that gets stored directly on the stack. While this works, it's a lot of effort, and given the number of images I needed to make the Wadness, it wasn't going to be easy to do it for every single one. But we know that pict is just a container format, and even though I couldn't figure out exactly how it worked, it's likely that the JPEG is just embedded directly inside unchanged. So if we diff the pict with the JPEG, we should figure out what is the pict part of the file. And in fact, when we do that, we get a distinct header and a distinct footer, and nothing else changed. Furthermore, if we diff two of these picts together, we notice that there's only two words that are changing between them. And these are both numbers that are direct offsets of the size of the image, which means they're just size fields of some form or another. Knowing this, it's really easy to write a script that takes the JPEG and turns it into a pict for us. Once you've done that, then you can just import the pict directly and then load it when you need it. This is what I did for all the images you see in the Wadness. In order to actually stitch the images together, I actually wrote some HyperTalk that would generate the scenes for me. Basically, you would tell it where an image was located and what was around it, and it would automatically program it with the correct click handlers and mouse key handlers on the card itself. This meant that I didn't have to go through the work of manually placing everything. I could simply keep track of where images were supposed to be and let my script automatically handle stitching them together. This was the first of several times where I had to use HyperTalk metaprogramming in order to make the Wadness work. Let's talk a little bit about how puzzle generation works. As I mentioned before, HyperCard doesn't have any color functionality built in, so we're only allowed to use Color Tools. Color Tools fortunately has an API, but I couldn't find any documentation for it. Instead, I had to go through and reverse engineer Color Tools to figure out what it supported. And the most important thing I found was that it supports the ability to color buttons. Now, it doesn't color the button itself, oddly. It just colors an outline where the button currently is. So if you have a button whose outline is a circle, you can draw a circle. If you have a button whose outline is a square, you can draw a square. And that's how we put together the puzzle. We used squares and rectangles for the paths, and then we used circles for the nodes. We colored them brown initially, and when you interact with them, we colored them yellow. Unfortunately, this means that we have to generate a lot of buttons, and we have to put handlers on each one of them. So once again, this means we need to turn to metaprogramming. This is the code that generates the puzzle. As you can see, it's a bit of a mess. Not only does it have to create hundreds of buttons, draw them, and write their code, but it also has to use globals to keep track of which nodes have been visited, which nodes are allowed to be visited, and what the current path is. Ideally, this would all be done on the card load, but HyperTalk isn't really meant like that, and the semantics are mostly oriented towards creating things ahead of time. So that's what we have to do. Messy or not, we now have all of the UI components functional and working together. What we don't have is any way to verify the user's solution. Now we could implement this in HyperTalk as well, but that doesn't necessarily make for a fun reversing problem. Instead, we want something native. Let's think about Color Tools. Clearly, they aren't doing anything in HyperTalk because otherwise, whatever APIs they were using, we could use ourselves. So instead, they must be using something native. And they are. They're using a foreign function interface called xcommands. Basically, what happens is you compile a binary against a certain library and attach it to the stack. Then it can call into the stack, and the stack can call into it, allowing you to implement far greater functionality than could be implemented in HyperTalk. Reasonably, you only have two options for xcommands. You can use C, old C, like really, really, really old C, like you really don't want to be writing this C, or Apple Pascal, which ironically is even older than the C. I ended up going with Apple Pascal because it turns out it's a fairly straightforward and easy to use language. I kind of liked it. However, it does have one catch. Unlike C, it doesn't compile to PowerPC, which is what this is running on. Instead, it actually compiles to the precursor of PowerPC for Macs, and that is 68K. Fortunately, 68K is fully emulated by PowerPC macOS. And at the end of the day, what is a CTF if not VMs on VMs on VMs? So we're going to implement our solver in Apple Pascal and link it against our stack using this xcommand library. Let's take a look at what that looks like. The Wadness was designed to be a reverse engineering challenge where they would have to analyze the solver that we write to figure out how to solve the puzzles. Once they do that, they get the flag. But in order for this to work, we first have to write the solver. This is the Macintosh Programmer's Workstation. You can think of it as the great-grandfather of Xcode. Now, MPW is quite the strange beast, not the least of which is because there's no terminal. Actually, you won't find a terminal anywhere on OS 9. Instead, it has text documents, and these text documents, if you so choose, can run bits of text as code. For instance, we can just run files here to get a list of all the files. This is the implementation of my solver. For those who didn't play the challenge, what this is doing is simulating a four-state automaton. Specifically, every time you move the path, it steps the automaton one further and then checks to see whether the path you just drew was adjacent to a red square. Don't worry about reading the code too closely. I'll make sure I publish it alongside the video. However, take a look at the import for hyperx command. This is the library that we'll be compiling against. Let's also take a look at the main function. We can see here how it interacts with hypertalk. Specifically, it gets passed in a handle to hypertalk, including function arguments and information referencing the calling context. We can then do things we want with this handle, such as call back to hypertalk, and then whatever our final result is, we have to attach it to the return field of this object. Then when we return, it gets passed back to hypertalk. We can go ahead and compile the program, and as part of that, it will automatically attach it to the stack itself. We're just about done, but before I show you the finished product, there's one more thing I want to talk about. When you compile a program on OS 9, it compiles it in a weird manner. Specifically, if you take a compiled binary out of OS 9 and try and look at it, it'll look like an empty file. This puzzled me for a long time until I noticed that OS X was still somehow recognizing it as a legacy application. And that's because what happens is, it compiles the code not into the main file, but into what's called a resource fork, a separate stream of the HFS file system. Because OS X, HFS, and APFS also support resource forks, although they don't use it, copying it out still preserves that. If you're using an operating system other than OS X, it will likely pull it out as a different file. This is why I would recommend using Stuffit for playing around, because Stuffit will properly handle the resource fork, and so when you pull it off, it'll ensure that all the data is kept. It's also why I distributed the problem as a Stuffit archive. You can also use ResEdit to play around with it inside of OS 9. This allows you to take a look at everything that's stored in the resource fork, pull it out, take a hex dump, whatever. And that's it. With our X commands done, the only thing we have left to do is connect them up to hypertalk, and after that our game is complete. The only other thing we need to do is actually generate the puzzles, which I did offline to ensure that they were unique. There's also a decoder, but all that's doing is taking your path, converting it into binary, and then XORing it with a predefined string. This is just so that we can't get any information about what the flag is until we've actually solved everything. Congratulations to the 24 teams who solved this during the competition, and I hope this was a lot of fun even if you didn't end up solving it. In addition to this video, I'll also publish all of the software I used and all of the code I wrote while working on this. Thanks again for watching. Please feel free to reach out with any questions or comments that might have come up. I had a lot of fun working on this and learned quite a bit. I hope you did too, and if not, well, I hope it was at least entertaining. Thanks again and enjoy the WATness.